These are the 8.3 notes, and we're going to be looking at estimating a population mean. So again, this is kind of building from we've been building this since chapter 6 really, but more so with the population mean from chapter 7. So it kind of stands to reason that if we looked at sampling distributions of sample means in 7.3, and we did the kind of reverse of that in we did the sample proportions in 7.2, and we did the reverse kind of the sample proportions to estimating the population proportion in 7.2, it kind of adds to reason that we're going to estimate a parameter of a population mean based off of a sample mean. So here we are at 8.3. So first of all, before we get into what a sample mean is, or before we get into how to estimate population mean from a sample mean, we've got to talk about t-distributions. So when estimating a population mean from a sample mean, it becomes more complicated in the fact that we don't know the standard deviation of the population. So with those proportions, when we did the sample proportions, we were able to kind of calculate standard deviations, and all we did was we just kind of filled in, okay, let's assume that the population has the same proportions as the sample, or we're going to assume that the population has a similar enough size to the proportion of the sample. So we'll just use the proportions that we have here to kind of be filler and estimates. Well, we don't have a formula like that for sample means, and in sample means we need to know the population standard deviation in order to figure out what our sampling distribution standard deviation is going to be. And when we just have one sample to work with, we don't have the whole population, we don't have that standard deviation. So what are we going to do? Well, what we're going to do is we're going to use the standard deviation of our sample, and we're going to place that standard deviation of our sample in for our when we look at the formula for standard deviation, when we looked at the formulas for standard deviation of a sampling distribution, so when we said the standard deviation of the x mean, we said that it was the standard deviation of the population over the square root of n, or the size of your sample. Now what we're going to do is we're just going to replace this, and we're going to assume that the standard deviation of the sample size is going to be equal to the standard deviation of our sample over the square root of n. So we've got one sample, and we're just going to take the standard deviation from that one sample, and we're going to replace it for the population standard deviation. The book has all the images for this, but when we do this t-distribution, if we work with a population that we know the standard deviation of, we know its population size, we know the population mean, so on and so forth. If we map out the actual sampling distribution with the real standard deviation versus the sample distribution with each sample distribution, we end up with a much different distribution, and that's kind of a complicated thought. And I don't want you getting bogged down in the details, because t-values are much simpler than their explanation. It's great if you understand how a t-value is created, but the explanation is much better. What we need to understand is, here's the basic premise you need to understand, is since we are moving from a standard deviation of a population we know to an assumed standard deviation of a sample, that standard deviation takes on a different distribution. It still looks normal in the center, but the ends, the tails of our distribution actually go out much wider, and they go out farther and farther and farther with the smaller your sample size. The larger your sample, the closer it looks to being normal, because with that larger sample size, we get less variability. The sampling distribution is going to approach normal each and every time we increase the sample size, and there's a certain point where it's essentially normal, not quite, but essentially normal, but we call this new distribution a t-distribution. And we say that a simple random sample of any size n has a t-value, which is the x mean minus the mean over the standard deviation divided by n, and it has a t-distribution with the degrees of freedom n minus 1. And this is very, very, don't get bogged down in the details yet again. So what does this mean? We're going to use t-values as our critical value. So if you think back to the population proportion, when we estimated a population proportion from a sample proportion, we use z-values because we're going to assume that most of those things are normal, and we had our rules for assessing normality, especially the biggest rule for the sample proportion was making sure you had 10 failures and 10 successes in a sample. We're going to assess normality here, and we're going to assume our sampling distribution is normal. We're going to learn those statements in a few, but what we essentially say is we've got a new chart now, and we're going to use t-values as our critical values as opposed to z-scores. And so we're going to use a t-chart to figure out what our critical value is that we're multiplying our formula by to figure out what our standard error is, or to figure out what our margin of error is. So here's what a t-chart looks like. This is table B. And basically what this is we've got the tails of the probability. So this like 0.25 here would relate to a 50% confidence interval. This point, because what I'm saying is I've got 25% over here, I've got 25% over here, so I'm looking at the middle 50%. This 20% suggests a 60% confidence interval. This 15% suggests a 70% confidence interval. 10%, 80%, 90%, 95%, 96%, so on and so forth. We double the amount here. I multiply that tail times 2, and then I do 1 minus that tail times 2, because that's suggesting on each side. So like with this 60%, I've got 20 on each side. With this 70%, I've got 15 on each side. With this 80%, I've got 10 on each side, so on and so forth. And so that's where I'm getting these intervals from. That 0.01 is 98%, 99%. And then we're really starting to like get into the weeds here. This is 99.5%. This would be 99.8%. 99.9%. And we can see some things here that make sense. We can see that as my degrees of freedom get larger, which suggests my sample size gets larger, these t-values go down. So my t-score decreases, basically saying the larger the sample size I have, the more confident I'm going to be in my answer, because when you multiply that error by a smaller value, your margin of error gets smaller. So we can see that as the sample size gets larger, we've got a smaller number we're multiplying by. We can also see that as our confidence interval increases, we have a larger number we're multiplying by. And again, this makes sense. We're thinking to ourselves, all right, if we want a larger confidence interval, that means that we have to multiply by a larger number. We've got to have a greater distance from our calculated sample mean here. We learned that in the last chapter, that in the last chapters, that as you have a confidence level that's increasing, as you want to increase that confidence interval, get larger, your confidence level will also go up. But with a higher confidence level, you have a larger window, you're not as narrow. So that also makes sense. And we can see here that if we've got a sample size of 1,000, we would expect, and we're looking for a 50% confidence interval. We don't have to multiply by much, because we're giving we're saying that 50% of our samples will have the sample mean in it. And we've got a really large sample size. And we can see here that if we've got a 99.9% confidence interval and we've got only like a sample size of only 2, then we have to multiply by a very, very large number, because we're not going to be able to narrow this down much. So this chart stands by that reasoning. All right, so let's go through and figure this out. We want to figure out what the t-value is for a 96% confidence interval for a random sample of 22 observations. So I go up, and we can see that where the confidence level is. I reported that up here with the tail value, but it matches down here with this 96%. So I'm going to go to the 96% confidence level, and since my sample size here is 22 observations, what that means is I need to go to 21, because this represents my degrees of freedom, so I need n minus 1, so this is 22 minus 1. I go to 21 for my degrees of freedom. I go to that 96% confidence interval, and I see that is at 2.189. So my t-value here is 2.189. A 99% confidence interval from 71. So I look here. 71, technically my degrees of freedom, n minus 1. 71 minus 1 is 70. Well, I don't have 70 on here. I go to the next closest lower. I don't jump up to 80. I always move down. So here the closest degrees of freedom I have to 70 is 60. So I'm going to work with 60 degrees of freedom. And I'm going to go to the 99% confidence level. And that is at 2.66. I believe so. Yes, that is at 2.66. So I'm going to say my t-value here is 2.66. And again, we can look at reasoning here. We can see that that t-value of the 2.66 that exists for degrees of freedom of 60 and the 2.639 that exists for the degrees of freedom of 80, that's not really a huge difference given the fact that there's a gap of 20 there. So rounding down from 70 to 60 is going to make very small difference fractionally. And if I did this calculation by itself, to get my margin of error, I would find that it's not going to be that much different than the calculator. It'll be a little bit different, but not too much. All right, so we've got some conditions for constructing a confidence interval about a mean. The first two are things that should be very familiar at this point. This should just always be assumed. Number one, it should be from a well-designed random sample. If we're not doing random sampling, we can't estimate the true population. It's always got to be a random sample. The second one is that we need to make sure that our sample is 10% of the population size. And again, when we get above 10%, we actually need to work with a better estimating because we've got such a large sample, we could get closer to the population mean than what these estimates give us. So if we want to estimate the sample mean using the methods that we're about to do, we need to make sure that A, it's from a simple random sample, and that we have at least 10%. So then we need the last thing, the population has a normal distribution or the sample size is at least 30. If you have a sample size that's at least 30, it's random, and you're at 10% of the population, go ahead, you can assess your sample mean right away. You don't even have to assess normality. If your sample size is below 30, you're going to have to assess the normality of that sample, and you're going to have to look at it because we're going to have no idea whether or not this sample is normal or not. And even if we do the sample could theoretically be normal, and we could be looking at a non-normal population, and our data could be skewed, but our best bet is to look at, okay, we've got the sample, let's see how close to normal this sample is, and let's go from there. Now, with assessing that normality, the book really leaves it vague. It says that when we're assessing normality, we want to make sure that the graph is close to normal. It doesn't have to be perfect because even if we're pulling from a normal population, sample size is at 20. Well, sample sizes at 20 could be a non-normal sample even if we're pulling from a normal population. If we're pulling from a normal population, we would expect a sample size of 20 to roughly be normal. So it doesn't have to be perfect. We're not looking for perfect normality as we did in Chapter 2. We're just looking for approximately normal. What is approximately normal? There's no set standard. It's kind of up for your own interpretation, and you're the ones who look at the data. You're the ones who basically make the statement. But when you're doing this on an AP test, if you're doing this for a job, you got to come up with a good defense of why you think it is or is not normal. You can't base it in like this just doesn't look normal to me. You have to clearly be able to explain it. Now from there, once we have all that, once we've determined that we've got a simple random sample that's 10% of the population with a sample size of at least 30, or our sample looks like it's fairly normal, then we can go ahead and try to get a confidence interval. We can go ahead and try to estimate what the population mean is to a certain confidence. Now there's two things here. We've got our standard error. Standard error of a sample mean is that standard deviation formula for a sampling distribution, but we're going to replace that population standard deviation of sigma with our sample standard deviation S of x. So we're going to go through, we're going to figure out what our data is, we're going to figure out everything that we've got, and we're going to use our sample standard deviation and the number of the sample size, and that's what standard error is. So it's basically saying the sampling distribution standard deviation, but we're replacing sigma with our sample standard deviation. And then from there, this looks familiar. It's a little bit different than what we did with the population because we're looking at sample means, but same concept. We take the sample mean that we found from our sample. We're going to add or subtract the t-value for whatever confidence level we're looking at, and we're going to multiply it by the standard deviation of the number. Again, I'm going to say this, and I've said this in class, I'm going to say it again, do not do this by hand. It's going to be frustrating. It's going to take time. Plug this in on your calculator. we have got the tools to plug this in on our calculator. We'll look at making these sample mean intervals via the tools in the calculator. All right, so check for understanding. Biologists studying the healing of skin wounds measured the rate at which new cells closed a cut made in the skin of an anesthetized newt. Here are the data from a random sample of 18 newts measured in micrometers per hour. Calculate and interpret a 95% confidence interval for the mean healing rate of the population. All right, so first thing that you'll do is you are going to plug all of this data in on your calculator, and you're actually going, because we only have 19 data points here, I believe. I've already plugged this into my calculator. Let me look again. So we only have we only have 18 data points here. So since we have 18 data points, we have to assess for normality. You're going to go on your calculator, you're going to do a histogram, a box plot, and a normal probability plot. We can review this in class if we're forgetting how to do this. It's also in the videos on my YouTube channel. It's the just calculator review. I have all of those things there. I've already done that, all three of them. They look roughly normal. My normal probability plot isn't exactly linear. There's definitely some change at the tails, but it's roughly linear. My box plot, it looks fairly even. It looks roughly symmetrical. My histogram looks roughly symmetrical. I've already done those three things. So with that, I'm going to say that this is roughly a normal distribution. It might not be exactly normal, but I'm going to assume that the distribution I have here is a fairly normal thing. Now, I do want a t-value, and this t-value is going to come from a degrees of freedom of 17, and then I'm going to look at the 95% confidence interval. So t-value 95% for 17 is 2.11. So I say that my t-value here is 2.11. Also, when you calculate this on you're going to have to put all this in your calculator because you don't have this. You need to do your first variable, first variable stats calculations here. I'm going to find that my mean is 25.67. And then here I use the S of X. I don't use the sigma of X standard deviation. I use the S of X because I'm looking at a sample. I'm not looking at the full population here. So this is 8.324. So now I can construct the actual mathematical principle here that my confidence interval is going to be 25.67 plus or minus 2.11 times 8.324 over the square root of 18. I use that full sample size. I don't use my degrees of freedom there. Now I can plug this in on my calculator. I can go through that math, but I'm actually going to go ahead and use the calculator function that I showed you in class on how to figure this out. So I'm going to go down. I'm going to use stats, test, and I'm going to go to 8, which is t interval. I'm going to use my input as stats, and I could have used data to begin with, but because I had to figure out if this was normal, I just used the other data I had. So I'm going to go to stats, and sometimes it'll autofill it. It's autofilled it for me of my X mean here is 25.67. My standard deviation is 8.324. My N is 18. And then my confidence interval here is 0.95. You might have to change that, but it's going to autofill data sometimes. Other times you're going to have to input that data yourself. So then I will go down, I hit calculate, and then it tells me my confidence interval. So my confidence interval here is 21.527 and 29.806. So then I can say we are 95% confident from 21.527 to 29.806 micrometers per hour represents average healing speed of skin of a newt. And that's a lot of words there. Again, we're describing that, but I'm going through that process there, and that's how I did it. I'm going to use my calculator for almost everything, but I still have this mathematical formula over here that I could use if we're struggling with the calculator instructions. I can plug all this in. The calculator does that for me, and I can figure out that, all right, we're not in 95% of sampling. 95% of samples at a size of 18 done randomly is going to give me intervals that have the sample mean in it. So I'm saying with 95% confidence that there is the mean healing speed of the skin of a newt from a laceration is about that. So there you go. All right, now margin of error and sample means. This is where it gets a little bit different because, again, to determine the sample size n that will yield a C% confidence interval for population mean with a specified margin of error, we have to get a reasonable value for the population standard deviation from an earlier study or a pilot study. This isn't like the proportions where we can just assume like, okay, what's the worst case scenario? Worst case scenario is like the 50% proportion. That doesn't work for us because worst case scenario is something like a standard deviation of 2,000. So when we have that standard deviation that we don't know, it makes it tougher. So what we do is we try to find an earlier standard deviation. If you're the first person running a study, best of luck to you, but 9 times out of 10, you're basing a study off of a previous study. So based off the margin of error you're looking for, you can make an assumption given the standard deviation of a previous study, and we can solve for that sample size from there. And then we're going to use the z-value from the normal curve for our confidence level of C. And we've looked at all those z-values. So again, let's go ahead. We've got this formula now. Z times the standard deviation of an earlier study over the square root of n has to be less than or equal to the margin of error. So administrators at your school want to estimate how much time students spend on homework on average during a typical week. They want to estimate the mean at a 90% confidence level with a margin of error at most 30 minutes. A pilot study indicated that the standard deviation of time spent on homework per week is 154 minutes. How many students need to be surveyed to meet the administrator's goal? So we want 30 to be greater than or equal to a z-score that relates to a 90% confidence interval. So again, I'll go to table A and figure out what has a tail of 0.05. And again, this is going to be about 1.645. That's the z-score that relates to a 90% confidence interval. This is going to be multiplied by the 154 minutes over my square root of n. So now I can go through, solve this inequality. I've got 30 divided by 1.645. So now I know that 18.23 has got to be greater than or equal to 154 over the square root of n. Multiply both sides by the square root of n. So that's the square root of n times 18.23 greater than or equal to 154. Square root of n greater than or equal to 154 divided by 18.23. N is greater than or equal to 154 divided by 18.23 squared. Plug that in on your calculator. And so we know that n has to be greater than or equal to 71.3. So we know that we need a sample size of at least 72. So we're going to say that we want to have a sample of at least 72 students to be able to say that our margin of error is less than 30 minutes, given the standard deviation of the previous study. Now again, that might not work out. Maybe we take the sample and the standard deviation is even larger than the previous pilot study. We're just working off a best estimate. This isn't a perfect science at this point, but again, we can say, all right, we've got this pilot study. With that pilot study, we're going to use their standard deviation. We're going to figure out what our sample size should be, and we figure out that we had at least 72 students that should be sampled for this. All right, you guys have a homework assignment tonight. Reach out with any questions or concerns. Have a great night.